Hello.
Hi, Detlef. Thanks for joining.
Hey, Kent. How are you?
All good, thanks. So we got another couple minutes, so we'll just give it until the hour, and then we'll officially kick things off. So just put you on pause. But great to have you joining.
Sure. Great to be here.
All right, we are at the hour, so I suggest we get things kicked off. Detlef, okay from your side?
Yeah, all okay.
All right, perfect. So I'll start off just with a quick introduction to kick off the session for today, and then I'll make you host so you can share your slides here as well. Really excited for today's webinar on the best practices in data analytics and machine learning. And really a privilege to have our speaker today with Detlef joining from BT. He is a distinguished engineer and the head of AI and data science research for BT's Applied Research Division. And quite an impressive background here. I'm not quite sure how you've been able to accomplish all of this, but I've published 3 books, over 120 papers, 15 patents, I think 30 additional patents that are pending. So I'm not quite sure if you don't get any sleep at night or if you're able to.
I'm old.
Okay. But a very impressive backgrounds, and I think quite rare we're able to get a bit of an insider's look of some of the cutting edge things that are coming and some of the best practices that are available to us today. So really looking forward to the session. For those of you joining, I really appreciate taking the time. We do have a certificate of attendance available. I see Andre has posted it in the chat already, and we'll continue to share it throughout the session. We will also be able to take questions and hopefully find some time for some answers as well. So if you do have any questions that pop up, please feel free just to drop them in the chat or in the Q&A section here in Zoom. So with that, I'm just going to, Detlef, make you a host here so you'll be able to share any materials that you have. So from my side, happy to support any way needed and pose some questions as we go along. But with that, I'll hand it over to you.
Okay, cool. Can you see my my screen okay, Kent?
Yes, perfect.
Okay, excellent. All right, yeah, welcome everyone. Thanks for having me, Kent. I'm going to talk a little bit about best practice in data analytics and machine learning and give you a flavor of how we do things at BT and some thoughts around how you should work in this space if you are after like responsible machine learning, responsible AI, and also how to get ready for AI regulation that is coming our way that is going to affect this whole area. Can I just see if I can get rid of this? Do we have a black bar at the top? Kent, that blocks the view?
No, I'm not. I just see your slides.
Okay, then it's good. Then it's just me.
Yeah.
All right. So this is a little scenario that I've come across when I was trying to figure out why we have a particular number in a report. And these numbers are typically called key performance indicators. So here, this was something about churn for a particular product. And I wanted to know why the report had a particular number in a particular week. Because when I calculated this number myself from raw data, I came up with a different result. And so what I dug a little bit deeper, and I found out that the way this number was computed was that we had a number of IT consultants that are working externally, and they produced reports by going into their own schemas in a data warehouse. They sent their results and tables to a fourth contractor who also pulled in data from an undocumented table in an enterprise data warehouse. Undocumented means in this case the column names are meaningless. So the column names were column 1, column 2, and so on. And this resulted then in a number which was passed on to a business owner of this particular key performance indicator, who then dutifully passed on this number to a spreadsheet owner, who collated it with hundreds of KPIs in one big report, which was sent out weekly to stakeholders. And these stakeholders look at these numbers and they make decisions based on these numbers. And the worrisome situation here was that I wasn't able to recompute this number. So I couldn't check if it's the same, because it turns out that the way the contractors computed the tables that are the basis for this information, they were overwritten on a weekly basis in their personal schemas. So there was no way to get back to older information and recompute a number for the previous week. So that means the whole process was not reproducible. We couldn't check if the number is actually reliable and correct. And this is obviously a problem when you use this sort of analytics for decision making. And this kind of informs the whole space, data analytics, data science, machine learning, because this is kind of a practice. This is rife across all industries. People are not tracking where the information comes from. They don't document the ways that they have analyzed data and come to conclusions. And if somebody wants to go in there and reproduce the results, it is often not possible. And this is why we need best practice in this space. And this really has to do with reproducible research. And reproducibility is at the heart of the scientific method. And when you analyze data, you're applying the scientific methods. You're doing actual data science, no matter if you do just analytics, create reports, or if you do complicated machine learning and build AI systems. And it's important that things are reproducible, and that means that somebody other than you can walk in your steps, can create the same results in the same way that you have done it. And that means you need to write everything down. You need to have the full computational environment available. That means code, data, everything. And this is basically the space in which we're operating and what I'm going to talk about. Let's have a little peek into software engineering, because this is going to be relevant to what I'm saying. When some of you might work in software engineering or are familiar with it, but when you produce software, then from a high level perspective, what you're doing is you gather requirements. From this, you derive specifications that describe what your software should be doing. Then before you start programming, you define tests. These tests will tell you if what you have programmed is actually to specifications. And then you write and document your software. Then you test your software until all the tests that you have defined before pass. And only if that happens, you know that you have produced something that you actually wanted to produce. And then you deploy it, and then you iterate. And these iterations are called continuous integration, continuous development, or they're called DevOps, which means you have software in production, but you keep refining it, and you keep producing new pieces of software that you test, and when the tests pass, you can deploy them. When we go to AI, machine learning, then what we're doing there is we're not just writing software, but we're using data and machine learning to automate decision-making at scale. Automation of decision-making is not new. We're doing this in IT automation as well. But in IT automation, you typically do this by writing down business logic and implementing it in software. So that's something that people have come up with, that people have thought through, and that you can go and verify. So you can go and read the software and check what actually has been implemented. In machine learning, that's slightly different because it is created from data. And I like this quote here: machine learning scales stupid. So if you make stupid mistakes, they amplify 1,000-fold through machine learning and through the deployment of machine learning solutions. This is a quote from Cassie Kozyrkov. She has a course at Google that's called Making Friends with Machine Learning. It's available on YouTube, and I really encourage you to have a look. So the difference when we build AI or machine learning solutions is that we're using data. And in that sense, data is like code for us. So while in a software product, the code defines the software, in a machine learning solution, also the code, but mostly the data defines the solution. And you could say that we are programming with data. The issue we have is that we nearly never really know our data. We only peek through it through a keyhole, if you like. And often we think all looks fine, but we're missing the bigger picture, and we might not spot the problems in our data that will replicate when we release a machine learning solution. There have been books written about this topic. This one here by David Hand, I recommend. You have to think, if data is your code for a machine learning solution, how do you find your bugs? So you need to check, is the data reflecting your objective? Is there bias in your data? Is bad history repeating itself? How trustworthy are the labels that you use to train your machine learning model? Have you defined the labels? Have they come naturally through some operational system? Or have they been done by a labeling service? And what do you know about the quality of the service? Is there malware in your data? You can have data poisoning, where data gets manipulated in order to create a backdoor in a machine learning solution. And there are also all sorts of other forms of what's called dark data, data that you don't see, that you don't know is there, or that you don't know is missing, or that you don't know has issues. So it's a very complex field, and you need to really pay attention to this and understand your data. Another aspect of data in machine learning is that while software checks its inputs, so here's an example where the email address that is put into the field is definitely wrong, and software typically picks these things up. So here, this is an attempt an attempt to SQL injection to hack the software. And you can pick these things up by checking what are the inputs. Are they correct in terms of format? Is it a number when I expect a number, or a string when I expect a string? Is the string having a particular format? You can check these things in software. That's different than machine learning. Machine learning is the ultimate garbage in, garbage out. Machine learning tool eats anything and will always come up with an answer. It won't, like software, say this input is wrong, and it won't say, oh, I don't know what that is. Here are a few examples from systems that have been trained to label images. And you can see these example images have been here labeled with terms. So this is like an ImageNet example. And these kind of tools that can tell you if an image has a dog or a cat in it. And you can, in the top row, you can imagine, okay, there are some structures in there that are similar to the items that are named as the label in the picture here. But in the bottom row, it's just noise, and you can't really tell why on earth would you come up with jackfruit for the fourth picture in that row. That's generally the problem with machine learning solutions. You cannot check if the input makes up the correct picture that you want to label, because that's what the machine learning system does for you. So you don't have any other way of checking it. and you need to take this into account when you release these solutions into the wild. Here's an example from a situation that I came across in the company, where a team of data scientists and software engineers, they tried to build a classifier that was supposed to predict this if a customer has a propensity to call us about a problem. And what they did is they built a naive classifier, a naive Bayes classifier, which is usually a very good classification model, very simple, usually performs really well. And they did this in R, a language for statistical programming, and they had numerical and categorical features. Then when they wanted to deploy it, they realized that they really haven't looked into the specifications properly, because the target environment meant that they couldn't run R in that particular environment. It was a big data environment running Spark. So they had to rebuild using a Spark library called SparkML. And this library can only use categorical features that are encoded as numbers. And the team interpreted this as numbers are fine, so it can use numerical features. And then it converted the categorical features into numbers and kept the numerical features as they were. But unfortunately, there were negative values in the numerical features, which meant that their method refused to accept these numbers. Otherwise, the method would have happily chewed through the data and produced some outputs, which would not have been correct. And so you can look into the description of these methods. You can see here that's the description of a naive Bayes classifier in R. And it tells you that it computes posterior probabilities using categorical variable, given independent predictor variables. And so you can see that the data frame X that is put into the method is a data frame of categorical and/or numeric variables. So that's fine. And if you look into the description of the method in SparkML, unfortunately, it's not that well documented. There's almost no text. It's just an example that the data consists of labeled points, and labeled points seem to be having a number, 0 or 1 at the beginning, and then there seem to be zeros and ones as a vector. But it's not really clear what these numbers mean, and the documentation doesn't say. And what it actually does, it encodes categorical variables in a one-hot encoding. So you need to convert it accordingly. And sometimes you're lucky that these methods tell you that something is not right with the data, but very often this sort of checking doesn't happen, and your method just accepts the data and produces some erroneous results, because you haven't made sure that you understand the data and the capabilities of these methods that you're using as your solution. And because a lot of the code that is being used comes from open source, then the developers often don't spend enough effort into documenting it. And so you're prone to fall into these sort of traps. So when we build a machine learning solution, then we could think about it, how do we manage this? And so is it like software, is it code? And we could say, yeah, it's code because it processes data and computes an output. So we should treat it like software. But maybe we should treat it like data because it's mainly defined by its parameters, right? A machine learning solution that could be anything from a decision tree to a deep neural network. And the parameters that inform the structure, they make up the essence of the machine learning.
Following the webinar, anything happens.
Sorry, somebody's not on mute.
Okay, how are you?
Oh, good. Oh, good. How are you?
Good. Yeah, the weather is that. Yeah.
Hey, Andre, I think you got off mute there for a second.
Yeah, starting to get used to that. So.
Sorry.
Yeah.
Andre, are you there?
So basically, can't.
Okay, I muted him.
All right, there we go. Sorry about that.
No worries. So it could be data. It could be code and data because it's an artifact created through a learning algorithm, which is code, which you probably got from somewhere. You haven't written it. using examples, which is data, which you got from somewhere, or you produce yourself, resulting in a parameter configuration, which is data, which you produced, that then determines how to compute through code new outputs. So a machine learning model is something complex somewhere between code and data. And that means you need to think about how you want to manage it in your organization. You could also have a data product view. You could say you need to manage the performance or the quality of experience, the usage, and you need to provide things like mitigation insurance for wrong decisions. So how do you do these things? These are the kind of considerations that you should have when you deploy machine learning. Then when you deploy a model, be it a data product or similar, how do you manage it going through its life stages? So as the first life stage, you have built the build stage where you develop it, where you should track data, metrics, parameters, artifacts, anything that is part of experiments that you run in order to analyze some data or produce some machine learning model. And you want to be able to package all of these models and machine learning projects so that everything is reproducible. That includes the software environment. Typically, you will use some libraries in Python and R or whatever language you use. But these libraries, they move on. So in 6 months' time, they could be completely different. Maybe there were some bugs in the current ones, or maybe definitions have changed. Maybe a method that could only accept categorical variables can now accept categorical and numerical variables, which means that maybe your old experiments don't run anymore. So you need to keep the libraries together with your code so you can reproduce what you have done. Then you go into deploy, commissioning, whatever code you produced. So you need to package it into batch or real-time serving platforms, or maybe you run it in an old school database. You may come across a variety of target architectures where you deploy your solution. It could be in the cloud, on-site, in operational systems, container, microservice, serverless, anything could be the target deployment environment. When you operate your model, you need to register and track the models through their life cycle. That means you need to monitor the data and the features that the model processes. And you ideally record every decision they make, what these decisions are used for, how valuable these decisions were, what the purpose is. So if something goes wrong, that you can go back and find out what actually happened. Remember, you won't be able to debug your model. You won't be able to have a look inside and say, why is this decision wrong? Typically, the machine learning models are black boxes, and you can't do that. So you can't just go in and fix code. You may have to rebuild them. And for that, you need the whole chain from build, deploy, and operate properly documented and preserved. At some point, you will retire. That means decommissioning the model. You may still have to archive it and the documented usage, because if somebody comes a year later and said, you made this decision, or maybe you made a decision about a person and this person has a right to explanation, you may have to dig all of that out and find out what you did back then and be able to explain it. To make things more difficult, the whole environment in which you operate these days becomes more and more complex. The machine learning code, the bit that the data scientist is responsible for, is the smallest piece of the whole puzzle. You have configuration, data collection, feature extraction, machine resource management, serving infrastructure, monitoring, all of these sorts of things that have to happen around a deployed machine learning code. This needs to be in place as well, and that requires new types of job roles and new types of tools. So we are no longer in a scenario where the single but genius data scientist comes up with a solution, deploys it, and runs it all by themselves. It is now pretty much teamwork with a number of different roles and responsibilities and a number of different tools. I mentioned MLOps. MLOps is the idea that you continue your development in machine learning. You may also call it production machine learning. It resonates with DevOps and software. DevOps meaning that you constantly develop and operate your software because you have a pipeline where you can inject new code that you have developed. It automatically runs through tests. If they all pass, then the software can be deployed automatically. And the same idea you would have in machine learning, with the difference that you may have to build new models through a new training process. But if you have this automated pipeline, then you can actually do this. You could constantly retrain and improve your models and inject them into deployment. In order to do this, to get these sort of automated environments, you may want to build yourself what's called an AI factory or model factory. And that's something that we have done in the company. The idea here is that you increase the productivity of data scientists and data engineers by increasing the number of models that they can produce and manage in production. So you want to take the kind of menial work away from them, so that they can concentrate on the creative piece, which means understanding the data, creating new features, testing the quality of the data, removing bias, these kind of things. This is something that data scientists need to do by analyzing and understanding the data in depth. But everything else, like, for example, building a model, you don't really need a manual model build process anymore. The libraries have advanced so much that models can be built fully automatically. They can be fully cross-validated and tested. And you can scale this to trying out many models at the same time. So essentially, the production of a model that performs to certain criteria can be done largely automatically. So in order to exploit this capability, you need these sort of factory approaches or pipelines. And yeah, let's have a look at what that could look like. We also want to make sure that we learn from software engineering and software development. So we want to use a test-driven approach. And this is sometimes called test-driven analytics. And you'll find a number of packages in different software languages that help you to do that. And the idea here is that you have capabilities to test if your data is any good, is your model properly validated and performs as expected, do the decisions you're taking have the expected business impact. All of these things you want to test. And in software engineering, they use test-driven development using automated unit tests. They have sophisticated environments for this. This is still lacking in machine learning and data science, but we can still apply these kind of ideas and methods. And here's a kind of a blueprint for such a model factory or AI factory that includes testing at every stage. So when you start, you always start with your data repository. And this is where you should start testing at the beginning. So if you can prevent bad data going into your repository, this is a big win. And all types of data repository allow you to do this. They allow you to script up tests against the data at injection point. So you can prevent incomplete or wrong data going into your repositories. You could even run continuous testing over your data to check for distributions, bias, and similar sort of issues, so that you are constantly aware of what is the quality of the data that I have in my repository. This also helps for operational situations. If you can figure out that your data quality is going down, that typically means you have an operational problem, which you can then address. Then from the data repository, you go into data wrangling. That means you prepare the data for analysis or machine learning. And this is the next stage where you need testing, in particular, because this is the first stage where you produce software. A lot of people ignore this because they think just writing some queries against the data repository is not software engineering, but in fact it is. The queries that you produce to change your data, to put it into different formats, to combine tables, you need to test it, that it has the intended effect. And this is also where you need to start thinking about versioning. And I'll mention this separately in a minute. Then you go into feature generation. This is where you might compute derived variables from your data. Again, you need to test this. Are the features actually as you expect them to be? And then you go into model building. This is where testing is largely automated these days. So you can just take a one-line script that builds your model using some library, and it can automatically do cross-validation. It can automatically do hyperparameter optimization. All of these things happen automatically in modern software, and the testing is already folded in. So you get some test statistics at the end that tell you what is the performance of what you have built. While you're in build, you should also think of versioning everything, obviously. This is, again, best practice from software engineering. You always write against the software repository like GitLab or something similar. And so you don't just write code on your own local machine and then lose track of what you have done. If you need to work in a team, it is much easier to work together if you are doing this by using a software repository, a versioning system like GitLab. And you can even think about versioning your data. So changes that happen to your data tables can be versioned. Not necessarily in the sense of that you're taking snapshots of your data tables every time, but you could have snapshots of the changes that have been done. And or you could have summaries of the changes that have been done so that you know in what way your data repository has changed over time. And if it's really important that you can roll back, then you need to do proper versioning and maybe go back to an earlier data version, if depending on your use case that is relevant. It is definitely relevant for the next 3 steps when you produce software to change your data or to build models. So then you go into production, and this should ideally fully automatically pull the latest model from versioning. So you should have a deployment pipeline where your data scientists just release a new model into the versioning system after it has passed all the tests. That can be done, again, fully automatically. And when this model has been kind of declared fit for purpose because it has passed all the tests, then your deployment pipeline can pull the latest model from the versioning system and automatically deploy it. You can run tests on this as well. So you can check if the environment in which your model runs is fit for purpose. Does it have enough compute power to serve all the requests? These sort of tests you should be doing here. Then model application means that your model now finally gets to see new data, and that this data goes through the model to make decisions. And you should log this. You should know what data goes through your model. And you need to test here as well. You need to check if the data that goes through your model is the same type of data that you have used to build it. And so this is the only chance you have to check against bad data going into your model. You can check for data drift and check for the distributions across your data being the same as in the training data. Then the model produces a prediction or an output. This typically informs the decision-making process in your business, which you should be logging. And you should then also check, this again is testing, does this decision have the desired effect? Does it give the benefit or the value that you expect it to give? Does that change over time? Is the model drifting away because people behave differently, the data has drifted away, or definitions in your data have changed? Maybe the model predicts kind of a fault situation, and maybe faults have been redefined. What was a fault a year ago is no longer a fault, or new types of faults have come into the definition, which your model doesn't know about. And one thing to do in this space is A/B testing. So you keep some of your data aside, don't run it through the model, and you see if the decision-making driven by the model has the desired effect compared to decision-making that you might do when you don't use the model, like the default decision-making that you used before. You can use the same thing for champion challenger models. So if you want to build a new model, you want to know if it's better, then you can run both models in an A/B test against each other, and you check which one is the better one. So this box here explains what sort of tests you can do at each step, what sort of errors you can test for. And just a note here, when you test anything for quality or impact, that includes checking for bias and fairness. So you should always check if your data is in any way biased. Does it over or underrepresent parts of the data? And what sort of effect does this have? If you make predictions or decisions about individuals, are they fair? I come back to this towards the end to go through an example of fairness checking. The environments that you're using or can use these days have changed quite significantly over the past few years. Most of the kind of analytics and machine learning happens in modern cloud environments. Here, this is a snapshot of Google Cloud Platform or GCP. And they have an environment called Vertex AI, which allows you to prepare data, train your model, and get predictions. And they also start to inject more and more governance around this so that you can track your models and log what they're doing and check for things like bias and fairness as well. One thing I'd like to point out is that cloud vendors also make machine learning available as part of query languages. So that means you can write an SQL query, for example, here in BigQuery. And in this query, you say, build me a logistic regression over some of the data. And that sounds very fancy and interesting, but the problem is that you open up machine learning capabilities to people who are not necessarily trained in doing machine learning. You create ad hoc models. You don't track them for quality because they're being produced outside of a well-governed area. And these things make a lot of assumptions, so particularly about the type of data that goes in there. And users may not be aware of the impact. So here's an example of a model that says it uses one hot encoding. And this has actually caused an issue in one of our machine learning exercises where people were not aware of this and then ran this particular model using one hot encoding over text data, wanted to categorize text data. And they were not aware, or it wasn't clear to them what one hot encoding means in this context. And that obviously didn't work at all. So that means this sort of democratization of machine learning needs guardrails. So you need to be aware who in your organization has access to machine learning and what can they possibly do with it. Can they build solutions using machine learning without you being aware of it if you're responsible for this? And where you then suddenly have models in production that are not documented and not properly monitored and tracked. There are a number of typical non-data science personalities or personas who need to analyze data in a business these days. And you have business analysts who are familiar with using spreadsheets and simple charts. They typically don't understand the complexities of data and data science algorithms. Typically, they cannot use SQL or write code. You have data engineers who build your data repositories and data pipelines. They are well qualified to use SQL and design data repositories. They have understanding of data quality and governance, can typically write some code, but they may not have understanding of data science algorithms and methodology. And you have software engineers who are used to write and test and version code. but they might not have the understanding of data repositories and data science methodology. And that means you need to be aware of these kind of roles and capabilities in an organization when you retrain them and use them to build AI or machine learning solutions. And the recommendation here is to refocus, to think about data science and machine learning as a collaborative workflow, not a tool. It's not about buying one environment in which you do everything. People need to be comfortable with visualizing data, and you need to support working with data visually, like through no-code environments, for example. And you also need to rethink automatic machine learning, called AutoML. A lot of cloud environments offer you automated machine learning, but that can cost you an arm and a leg if you're not careful. So you can very easily just point these environments to a large data set and say, find me the best model, and then you let them run, and you create a huge compute bill at the end. So typically, you should be very modest with your resources that you're using. You always should try and find the simplest model first that works, and not go for the most accurate. Typically, the last few percentage of accuracy may not be worth the money. And then in this sort of space, you need to think about how you support automated testing of data to make sure you have good quality data going into the process. Versioning and reproducing ad hoc workflows that are created through trial and error. How do you do this? If your people run experiments on their local machines and then say, oh, I found what works, then how do you from there go into version? How do you make sure you can build it again? And how do you constrain machine learning and make it safe to use? And I'll have a few more remarks on that going forward. So let's have a quick checkpoint. Let's say we want to build a machine learning solution, and we want to make sure that whatever we do is fair. Fair in the sense of we're not discriminating against maybe parts of the population or particular individuals with a certain background. And this is widely discussed these days. You probably came across the discussion around bias in AI. If you're not familiar with the Algorithmic Justice League and with the work that Joy Buolamwini has done, I really encourage you to look that up. And you'll find that checking a system for fairness is not just checking some metrics. It's as much about social justice as it is about removing bias from data. So you need to ask yourself who collects the data, who writes the code, who operates the AI, who is targeted or who has access to the AI, and who's auditing the AI. All of these dimensions impact on the fairness of a system that you produce. And what you see as the technical side of the solution are fairness metrics. And here's one example called Disparate Impact, which measures if two groups are treated differently through an algorithm. And there are lots of these fairness metrics, and unfortunately, they're mainly incompatible with each other. So that means you can be fair according to one metric, but completely unfair according to another metric. So you really have to decide, what does it mean to be fair? And that's not something you can decide technically. That requires the business stakeholder to say what is fair to them. What do they think should be fair in this solution? And you can use, for example, the IBM AI Fairness 360 tool that IBM has produced and released. This is a really great tool, but it already offers you more than 70 different metrics in the GitHub repo that you can use to measure fairness. So which of these should you use? How do you figure out what makes sense? And you can have very weird effects when you test your models for fairness. And here's just one example. So the fairness metrics work either by changing the data to get bias out of the data, making the distributions fairer. You need to pick an attribute that you want to be fair about. And here for this particular example, we used a public domain data set. It's called the adult data set, which is about giving loans to people. And we used gender as the attribute that we wanted to be fair about. And so now when you use the fairness metric, you usually have to say, how fair do you want it to be? So you need to define a threshold. And here in the image on the left, you see what the accuracy of the resulting model is if I use different thresholds for the fairness metric. And the interesting thing here is that the accuracy is very volatile. It goes up and down constantly. So if you change this threshold for fairness only slightly, you might end up with a completely different level of accuracy. It might go up, might go down. It also means when you deploy your model that you have built towards a certain fairness threshold. The fact being that new data is typically slightly differently distributed, you will get a different performance. And so you need to keep checking this in deployment while you're using your model to make sure that your fairness and your accuracy is still as you want it to be. The right-hand side illustrates the incompatibility of fairness metrics. So here we used one fairness metric to make the model fairer. And the blue line shows the modified model after we applied the fairness treatment. And you can see here low is better. So a lower value means less difference between the two classes, the two genders. And you can see that at some classification threshold, this fairness kicks in as you would expect. But this threshold can be at different places. So we have different splits between training and test here. And we just ran a few hundred train test splits to see what different results are we getting. And you can see that the lowest point of the blue curve is at different classification thresholds. And you can even see in the bottom that the unchanged model, which is the red line, it's the same throughout the pictures. Not the same because the train test splits even there give you different performance, but you can see that in the bottom case, the unmodified model is fairer towards this metric than the one where we changed the fairness according to another fairness metric. So you can get these weird effects, and you really need to be aware of it and very carefully analyze this and monitor this in deployment. The question is, what could possibly go wrong when you do this? And this is something that you need to look at from a corporate governance perspective. The business leader is really responsible for the performance of anything that is deployed in operation. And so business leaders need to set their red lines. What is it that they want to release? And what is the performance and the kind of bias or fairness that they can tolerate? Then you need risk and governance teams in an organization to implement and control these processes. A product owner will be responsible for what is being built, and they need to identify and own the risk of this AI product. And the role of the data scientist would be to describe limits, restrictions, and assumptions. So what is it that they have built? How should it be used? How should it not be used? And make this very clear through documentation. And so this is the whole envelope of AI governance, and it needs to be enforced by a diverse team with diverse roles and backgrounds. You can't leave this to data scientists. In BT, we have created a framework for this, which we call the Responsible Tech Framework. And this governs also our responsible AI approach. And from this framework, we decide, okay, what we do is for good. We are accountable, we are fair, and we are open. And this then determines the governance framework that we apply in the whole machine learning process. All right, I think I should stop here so we have some time for questions.
All All right, perfect. Well, thanks for the very informative overview. Learning a lot on my side as well. A number of questions just coming in, and for any of you looking to post some questions, feel free to just drop them in the chat, and we can pick them up. There were a couple questions that came in around, if someone was new to machine learning or the data analytics side, do you have a recommendation of a good starting point to actually start to learn about these topics and get a bit more familiar with them?
Well, there are a lot of training courses available. Lots of them are free. So there's one site that I use a lot. It's the KDD site. I'll find the link and put it in the chat. This is they keep lists of training courses that are free, but you can also go into the standard systems like Coursera and others that offer courses. Sometimes you may have to pay a fee, but probably if you pay a fee, you get more quality. The cloud vendors, Google, Amazon, they all give courses. So some of them, again, free. A good starting point is the course by Cassie Kozyrkov that I mentioned. It's available on YouTube. You find it when you look for Making Friends with Machine Learning. This is like a 6-hour course, which already gives you a good overview of the kind of things that you should learn. But in particular, if you want to work in that space, you should have a solid background in kind of mathematics, statistics. It's the most important thing, because you will have to look at data and you will have to apply tests, and you will have to understand what distributions in data mean. And so I would always start there. I recommend to start there. You don't really need to start with understanding how to build neural networks, these kind of things. This is not the right way. I would start statistics and math, and then work my way up into introductions to machine learning.
Excellent. So some good advice there. There was also another question. Looks like one of our attendees is looking to do some experimentation with a model, and they're asking if you know of any free platforms that they can host a model and do some short-term experimentation.
That would be Google Colab.
Google
you
Colab.
Can go into Colab and you get yourself a free notebook, and you can run Python and R code and do some experiments.
Very good. So hopefully that'll be helpful. Looks like they're looking to do a model around some data they're getting from some sensors. So hopefully that's an area that they can experiment with. I mean, Detlef, you've obviously spent quite a bit of time with your PhD and postdoc, becoming a real expert in this area. I guess for those attendees that may be looking to obviously go to university and become a bit more expert, but not necessarily want to go the whole PhD postdoc route. What are some interesting roles in the field that you don't necessarily need to be an advanced expert on, but can still be in this area?
Yeah, I mean, there are loads of roles these days in that space. So the data engineers are looking after data repositories and basically putting data into a shape that stakeholders can work with. So if you're interested in this, these are typically people with a background in things like SQL or data pipelines in cloud environments. If you want to look up these courses, you'll find that. Then data analysts. So not everybody has to be a data scientist. Most of the work is done in creating reports and collating data so that it is informing others, giving insights for decision making. And that means you need to be able to query data repositories, work with tools like Excel, or maybe dashboard tools. If you want to experiment with dashboards, you can use Shiny if you work with R, or you can use Dash if you work with Python. These are free libraries that you can experiment with. And this is then about how to present information to stakeholders so that they can make sense of it. So visualization, graphs, these kind of things. Then if you want to go into machine learning, then yeah, as I said, the key kind of capability that you need is to be able to look at data and understand what the data is about. And that typically means at least basic statistics, things like what are averages, variances, what are distributions, what are correlations, these kind of things, and then be able to run some statistical tests that allow you to figure out maybe if two variables are related or independent of each other, these kind of things. And so an introductory course in statistics is useful. And then to get more familiar with machine learning, you can then look at different machine learning libraries. So in Python, for example, there's scikit-learn, and you can work your way through these tutorials and then maybe do some courses and get some certificates in online training environments. There's Kaggle if you want to sharpen your skills. Kaggle is an environment where you can apply machine learning to different data sets and join competitions, which then helps you to figure out how good are you in solving these problems. So there's a variety of roles. You can also be like a product owner who looks after machine learning experts. So that means you don't need the skills to build things yourself, but you need to be able to manage people in technical roles and make sure that they work to certain standards. You can have a social science background and look into the kind of responsible AI, ethical AI. How should we use AI systems? What sort of decisions should they be allowed to make? How do we regulate them? How do we govern them? And it's more common now in organizations that data teams are diverse and pull in people from different roles, different backgrounds, because that's the only way to figure out that you might do something that is not quite right, and where a use case, maybe you shouldn't be touching the use case and you should do something different, or you come across issues that maybe as a technical person you wouldn't see, but somebody who looks at it from another perspective can identify. So there's a lot of opportunity in working in AI.
Excellent. Well, lots of great starting points there, or entry points, I should say, into this field. Yeah, it's great to hear. Yeah, and I think you may have covered this in your answer just now, but there was a couple questions around, what coding languages, whether it's Python or R or the different libraries. Any advice from your side of kind of where to focus on the learning, or is things changing pretty quickly now?
Well, yeah, things change quickly because you always get new libraries. But if you start with the basics, then you can always catch up. So that's why I'm saying understand the basics of statistics. If you want to go into machine learning, then understand the basics of machine learning algorithms. And importantly, what is it that they actually do? Then once you're familiar with one of these libraries and you understand what they're doing, you can very quickly pivot to another one. This is typically just maybe a different scripting language, some slightly different flavor, not difference in terms of kind of technology, if you like. The more difficult end of the spectrum would be systems like deep networks, TensorFlow, these kind of things. And so for this, you should have a solid mathematical background. So start there first. You need linear algebra, you need statistics to really understand what these systems are doing, and so that you have some control over these algorithms and not just experimenting. I put the link into the chat, by the way. It's kdnuggets.com. This is a good kind of site to look for blogs and pointers for free resources.
Perfect. Yeah, I see it there in the chat as well. So thanks for dropping that in. Yeah, I know we have just a few minutes left, so a couple questions left from my side. I'm guessing BT is using all sorts of various models that are at various different points in the process that you mentioned there. I'm curious, like, what are some of the main models or use cases that BT is actually using when it comes to machine learning?
Yeah, I mean, not many people know this, but BT is doing research in AI for over 25 years. And we have deployed a number of internal solutions. So most of our AI works internally on our processes and systems. So for example, we have a large AI system that is based on optimization and search to run our mobile workforce. So all the jobs that are sent to mobile engineers to make sure the right person turns up at the right job at the right time is managed by one large AI system that is already in use for 20 years. We're doing AI for fault management in networks. So we look at telemetry that comes out of the networks. We do anomaly detection on top of it, which is kind of a statistical method. And then we see if these anomalies, when we detect them, are they predictive of certain types of faults, and then see, can we do something to prevent these faults from actually occurring? So we can deploy engineers quickly before some device breaks down and hundreds of people lose broadband. So this would be a typical use case. We are doing a lot in cybersecurity, where it's mainly around understanding data. So we use AI to reduce the massive amount of data that cybersecurity specialists have to look at to identify security breaches. And we call this a human in the loop system, right? So the experts use AI to reduce the amount of data intelligently and then spot the unusual patterns that might be indicative of security breaches. We also do AI and marketing, so, the typical kind of advertising or churn prediction, these kind of things we do. And we have one solution that is given to our consumer market, which is a spam filter for phone calls. So we are trying to identify nuisance callers in our landline product. And again, this is done through anomaly detection. It's also a human in the loop system. So we identify calling patterns that look suspicious, and then experts identify them as spam caller, yes, no. And if they are identified as a spam caller, they are redirected into a voicemail box. So instead of ringing at your house, you get a call into an answering service. So you can still later check if it was something genuine, but we're pretty good in stopping these sort of spam callers.
Fantastic. Well, great to hear such a long history of this at BT, and I would have been at really the cutting edge of this for a number of years now. So very, very impressive. I see we're just at time, so lots of kind words coming through, thanking you for the presentation and the overview. I certainly learned a lot, and likewise from my side, I really appreciate the time and sharing with us some of your knowledge as well. And just to wrap it up, Detlef, I'm assuming we can get the slides from you, if that's okay.
I'll send them.
Perfect. And we'll share after via email the slide deck, the recordings of this, and a link to the certificates in case no one got that as well, so that you're all covered. Once again, I really appreciate your time. Thanks everyone for joining, and wishing you a good rest of the day.
Thank you very much. Thanks for having me.
All right. Thanks again. Take care.
Thanks. Bye.